Hello, my name is Brian Morgan. I am a senior associate and structural engineer at Magnus & Clemensic Associates, Seattle, Washington, United States. I'm a structural engineer for the Capitol Commons projects, Green Hills projects, and Circular Verde projects. The Philippines in general is a high seismic region. It's part of the Ring of Fire. In addition, it's very active from typhoons and high winds. The West Valley Fault runs through Metro Manila, and it is seismically active. But in addition to that, there's many other earthquake hazards that are nearby. There's the subduction zone further out in the ocean. The goal of any design, high-rise or otherwise, is to provide a safe, habitable building that can resist these natural forces upon a structure. So we have engaged some of the world's best consultants to help us determine the seismic hazard at all of these sites. When we design for a building that's close to a fault, we're actually not designing just for a particular earthquake that might occur on that particular fault. We're also including faults that are 200 kilometers away that might be able to produce a larger earthquake, for example. So all of these faults go into very advanced computer modeling and prediction and develop a seismic hazard specific for that site. Yeah, so the Royalton at Capitol Commons, the buildings are constructed of reinforced concrete construction. The lateral system of the building is a central ductile concrete core, the spine of the building, and extends all the way down to a reinforced concrete mat foundation that is socketed into the rock. As the earthquake were to come to the site and move, you would anticipate this building would sway and move and deform, absorb that energy. And the ultimate goal is we do not want these buildings to be collapsing under these earthquakes. We want them to be able to resist these earthquakes in a predictable manner and maintain stability for the residents inside. So the Imperium is very similar. Again, it's concrete construction. It is a more slender building than its counterpart, the Royalton. It uses a similar concrete core system, but it also utilizes an outrigger system to give it greater stability. What you'd anticipate in this building is that, again, its stiffness and strength are adequate for moderate and large wind forces. Under a very large earthquake, you would anticipate that the building would react and rock and absorb that energy through yielding of the buckling restraint braces. So these elements are meant to yield and meant to absorb the energy of the earthquake and limit the damage under a large earthquake. So Maven, again, is reinforced concrete construction. The two towers, one of them is approximately 200 meters tall, the other is 130 meters tall. The buildings will use this shear wall, core wall system as its spine, its stiffness. When lateral loads from wind or seismic hit the building, the core resists these forces. It has adequate strength, it has adequate stiffness, it has adequate ductility, so that when a very large earthquake event were to occur, the building moves and rocks and absorbs that energy dissipation, and then absorbs that energy and dissipates it. Rather than crumbling and failing, it absorbs it through movement, and the goal is to have a building that's safe and standing at the end of a very large earthquake. So the Viridian at Green Hills is a tall high-rise building. It's constructed of reinforced concrete construction. The lateral force-resisting system is a central concrete core that houses the central services of the building, the elevators and the stairs. It's the spine of the building. It's founded upon a reinforced concrete mat foundation into the rock, a very stable system to take the forces down into the soil. In addition, The building utilizes an outrigger system with buckling restraint braces. The intent of that is to provide greater stiffness and stability of the building, a greater stance. And the detailing of that is such that under wind and moderate seismic, the building is intended not to yield. It's intended to have adequate strength and stiffness to resist those forces. But under a very large earthquake, what you would anticipate is that these buckling restraint braces are intended to yield. Their goal is to yield. Their goal is to absorb the energy that would be imparted upon it, such that under a very large seismic event, the building is able to move and react and absorb the energy such that you have a safe building that's habitable and can withstand aftershocks and is not collapsed. So Avila at Circular Verde is a reinforced concrete structure. It's 2 towers that are interconnected. They're not intended to be standalone buildings. They're intended to work with each other. They're connected at the 28th and 30th floors such that under lateral loads, the 2 buildings will act as one. They will share the load and they will resist the forces. So under wind and seismic load, the building, you would anticipate it that it will react and move and sway under those demands. The goal of which is to have a safe, habitable structure after an earthquake event. Given the very high seismicity of Philippines and the very high wind demands that come from typhoons, it was important for us to engage other experts in these fields. So we reached out to an international consultant, Langan Rollo, to help us with the geotechnical aspects of all of the sites. It was important to help us define the seismic hazards specific to each site such that we could design the building uniquely for that site and appropriately for that site. In addition, we engaged a wind tunnel consultant, RWBI, out of Canada, to help us find the wind loading specific to each site. Not only specific to each site, but specific to how the buildings will interact with each other. A building standing alone behaves differently than a building amongst a forest of other buildings. And so with these consultants, other international consultants on our side, as the structural engineer, we were able to get very specific and unique demands and loads for each site, both from a seismic and wind perspective, and design the building safely to meet those demands.